Hi, this summary will be the last summary of the chapter 1, that is sequences and series. Now we will summarize the power series, Taylor series, Maclaurin series and some applications of those series. First, we want to give the definition for a power series. A power series, if you note here, that is a series not with constant terms, but also it includes a variable term x. That's why this is not the same as the series that we discussed up to now, and we say that a power series is a series of the form and from 0 to infinity an times x minus c to the power n, where this series is called a power series about the point x equal to c, or a power series in powers of x minus c. If we consider term by term computation of the series, note that the first term does not have a variable x, because if you put 0 for n, it gives us a sub 0, and other terms are also obtained there. One of a basic example of those series is the geometric power series sigma 0 to infinity x to the power n, where we know that a geometric series converges if and only if absolute value of r is less than 1. Here x stands for r, then we can say that this geometric power series converges if and only if absolute value of x is less than 1, or if and only if x lies in between -1 and +1. For the convergence of power series, we have a basic theorem which says that one of the following is true for a power series. Those are that the series converges for every x in R, that's for all real numbers, or the series converges only for x equals c, which is called the center of the convergence series, and this convergence is called the trivial convergence. Or the third one, there may be an interval c minus r, c plus r, which is given here as absolute value of x minus c less than r, and the series converges absolutely for every x satisfying this inequality, and other cases are also mentioned here. In this definition, or theorem, there is a number r, where this number r is called the radius of convergence, c is called the center of convergence, and the interval on which the series converges is called the interval of convergence, and it is represented by I. If the series converges only at x equal to c, in this case the radius of convergence is 0. If the series converges for every x in R, that's for all real numbers, then the radius of convergence is infinity. And if we want to test the convergence of a power series, note here that we either apply the ratio test or root test on the absolute value term of the series, that is for the series sigma 0 to infinity absolute value of an times x minus c to the power n. Since those are given facts related with the power series, I think we can obtain an example where example says that find radius of convergence, center and interval of convergence of the power series. If we go through the solution, in this case we have ratio test which is applied to the series sigma an, and it gives us absolute value of x plus 2 as limit n goes to infinity. So we are saying that the series converges absolutely for every x satisfying the condition that absolute value of x plus 2 less than 1, and divergent conditions are also given. But this is not all, but also at the endpoints of this open interval, a power series may converge or diverge, where those cases should be checked one by one. For example, if x equals to -1, then this power series x plus 2 to the power n over n plus 2 becomes the series 0 to infinity 1 over n plus 2. But if you note here that this series is written as the sum of two terms, such as 1 over 2 plus the series not from 0 as the initial value of n but 1 to infinity 1 over n plus 2, where this series sigma 1 to infinity 1 over n plus 2 diverges by limit comparison test, since the terms of the series 1 over n plus 2 is positive and 1 over n is positive. If we consider the limit of this ratio 1 over n plus 2 over 1 over n, which is 1, and also we know that the harmonic series 1 to infinity 1 over n diverges, so we are saying that for x equal to -1 this series diverges, means -1 is not in the interval of convergence. Once more, I want to take your attention to the point that the series given starts with the initial value of n being 0, but we change it and we write 1 over 2 plus a series from 1 to infinity, because in this case for limit comparison test we want to use the harmonic series 1 over n. Certainly 1 over n is not defined for n equal to 0. That's why we use the series 1 to infinity, but since the series 1 to infinity 1 over n plus 2 diverges, if you add a constant there, certainly it also diverges. If you consider the second boundary point, -3, when you put -3 for x in the series, it becomes the series 0 to infinity -1 to the power n over n plus 2. Certainly this is not absolutely convergent. It is known from x equal to -1 case. And if we consider bn times bn plus 1, this is negative. So this is an alternating series. And the conditions for alternating series, first and second conditions, are satisfied. Therefore, we can say that the series n from 0 to infinity -1 to the power n over n plus 2 converges by alternating series test, which gives the result that -3 is in the interval of convergence, where now we can write the interval of convergence. It is the interval closed at -3 and open at -1. Radius of convergence r is 1, where the center of convergence c equals to -2. By this way, we solve this example. After this example, let's have a theorem where it says that we have two power series, both converge on their radius of convergence, and then we can say something more about the power series. In this case, the first condition is constant times the general term. Then we can take the constant outside the sigma notation, and the radius of convergence of these two series are the same. In the second, we may add these two power series, or if a series from 0 to infinity an plus bn x to the power n is given, it can be written as the sum of the two power series an x to the power n plus bn x to the power n, certainly with sigma notations. But this equation holds. We have to be careful here that this equation holds if both series sigma an x to the power n and the series n from 0 to infinity bn x to the power n converge, where the radius of convergence for the sum in this case is a real number which is larger than or equal to the minimum of r sub a and r sub b. So by this way, we just mentioned about the sum of two power series, or a constant times a power series. But the next theorem is a useful and an important theorem. In this case, we are saying that if we have a power series, an x to the power n, and from 0 to infinity, which converges for every x in the open interval minus r, then the important part maybe is here. This power series in this case defines a function on the interval minus r, or f of x equals to this power series for every x in the interval minus r, where we now can say that this function f is differentiable on this interval, and this differentiation is made term by term differentiation, where the obtained new function f prime of x, that's the derivative of the function f, is a series where the initial value is not 0 but 1, and the general term n times a n times x minus x to the power n minus 1. But this derivative function in fact is defined for every x in the interval minus r. But more than this one, or furthermore, we can say that this function in fact is integrable on the interval 0x. Again, this is term by term integration, where obtain new series, power series, and from 0 to infinity a n times x to the power n plus 1 over n plus 1. This means that using differentiation and integration, we can find power series representations of some functions. If we consider the example, it says that find the power series representation of arctangent x. In this case, first we start with the geometric power series, which equals to the ratio 1 over 1 minus x for every x in the interval minus 1, 1. Now, if we consider minus t square in the interval minus 1, 1, and if we put that for x in the geometric power series, we obtain a new series, power series, in terms of the variable t, where 1 over 1 plus t square in this case equals to the sum from 0 to infinity minus 1 to the power n t to the power 2n. And now if we integrate both sides of this equation, the left hand side and the right hand side, on the left hand side we obtain arctangent x, but on the right hand side in this case we obtained the power series, and from 0 to infinity minus 1 to the power n x to the power 2n plus 1 over 2n plus 1, where it is again defined for every x in the interval minus 1, 1. Means that we get the power series representation of a function. Now if we turn back to the initial point, that is this point we started with defining a series, there we start with this words that sigma an is a series with constant terms. Then we discuss the power series sigma n from 0 to infinity an x minus c to the power n, with general term an x minus c to the power n, containing the variable x. And using geometric power series, we obtain power series representations of some functions. But now we may ask the following questions. Question: do all functions have a power series representation? To answer this question somehow, we will mention about Taylor and Maclaurin series, where a Taylor series is a series where I will tell it later, but now we will just say that if a power series an x minus c to the power n converges to a function, then ak is the kth derivative of the function at the point c over k factorial, where the proof of theorem is given here explicitly, but I don't want to say more about it. But what I want to say is the definition of Taylor series and Maclaurin series, where in this case Taylor series is the power series and from 0 to infinity, and derivative of the function fn at the point c, that's the center, over n factorial times x minus c to the power n. If this constant c is 0, most of the time this series is called the Maclaurin series. And if we say that the sum k from 0 to n, kth derivative of the function at c over k factorial times x minus c to the power k can be written as a polynomial of nth degree, where we represented this sum by p sub n of x, which is called the Taylor polynomial of the function. After this one can easily understand that every function has a Taylor series representation, but this doesn't mean that every function equal to its Taylor series. Once more, I want to say that every function has a Taylor series, but the function may not be equal to its Taylor series, where this equivalence condition is given by the Taylor's theorem, because in this case we can write a function as the Taylor's polynomial Pn of x plus En of x, which is called the remainder term or the error term. But we have to be careful that theorem guarantees some number between c and x, which is t, and En of x is the nth plus first derivative of the function obtained not at c but t, where t, I want to remind you, that is a number between c and x, over n plus 1 factorial times x minus c to the power n. Now if you take the limit as n goes to infinity, the both sides of the equation f of x on the right hand side, which equals to Pn of x plus En of x. In this case, if En of x goes to 0 as n goes to infinity, then one can easily notice that Pn of x in this case becomes the series k from 0 to infinity fk of c over k factorial times x minus c to the power k, where in this case we can say that the function equal to its Taylor series. So this can in fact be expressed by the words that f of x equal to its Taylor series if and only if En of x converges to 0 as n goes to infinity. So if you consider the note once more that En of x goes to 0 as n goes to infinity for every x, then f of x equals to its Taylor series. Now I want to give a definition where it says that a function f is an analytic function at the point c if its Taylor series about c converges to the function itself, where for the analytic functions we have given some examples of the analytic functions, such as e to the power x equals to the power series x to the power n over n factorial. Sin x and cosine x are also given some examples of Taylor and Maclaurin series. We mentioned about the Taylor series because Taylor series has applications not in mathematics but in the areas which is related with the mathematics. We can have some applications of the Taylor series where we are saying that there are many applications in the mathematics and related areas, where some of them we may approximate the values of functions, we may evaluate the integrals which cannot be integrated by elementary integration techniques, or we may evaluate some limits of indeterminate forms, where it may not be easy to evaluate by the method of computation for the limits. If we consider an example in this case, we define a function e of x, which is an integral from 0 to x sine t over t dt. And if we want to evaluate e sub 1, which is the integral from 0 to 1 sine t over t dt, with an error less than 1 over 10 thousandths or 10 to the power minus 4, then we can consider the Maclaurin series for sine t, and then we can divide it into t. Then we obtain the power series, and from 0 to infinity minus 1 to the power n over 2n plus 1 factorial times t to the power 2n. Now if we integrate the right hand side and the left hand side is the integral from 0 to x sine t dt, but the right hand side is obtained in the last row in the scene. Then we compute the Maclaurin series of e of x, but if you put x equal 1, it gives us e sub e of 1, which is the integral from 0 to 1 sine t dt, where this is an alternating series, and we know how to compute the alternating series with some error, where the computation is done here. And it seems that if n is larger than or equal to 2, that is, if we use the first three terms of the series, we can approximately compute the integral from 0 to 1 sine t over t. But I want to remind you one more thing. If you note here that sine t over t at 0 seems that it's an improper integral, but this function has a removable discontinuity at t equal to 0, so it is not a improper integral, where the approximated value of this integral in this case is given in this solution. Another example is the evaluation of the limit x goes to 0, 1 minus cosine x over x squared. In this case, again, we can write the Maclaurin series of cosine x, which is 1 minus x squared over 2 plus x to the 4 over 4 factorial minus and so on. And if you simplify this ratio, then we have the limit x goes to 0, 1 minus x squared over 4 factorial plus x to the 4 over 6 factorial and so on. And if you put 0 for every x, it gives us the value 1 over 2. So by those discussions, we completed the reviews and the discussions on the series, or on the first chapter also. So we hope you will enjoy your classes.